Okay, so first of all, I would like to thank the organizer of this FDP on hands-on training in computational material science for inviting me in this particular workshop. So this, as I can see, that this is the workshop or a faculty development program, which is basically focused on the hands-on training in the computational material science. So today, actually, I am going to talk about the fundamentals of the density functional theory, because this particular theory is the main building block of the whole this computational studies, computational modeling of materials using some softwares. So if you see, hello, I hope I am audible, huh?
Yes, sir. Audible, sir. Sir, Ashok, sir, unmute yourself, sir.
Hello,
Yes, sir. Now you know.
I'm audible now.
Yes, sir. Audible.
Oh, okay. Okay, so if you see this particular structure, this cartoon here, so we have the first part, then middle part, and the last part. Okay, so first part we have some structures like graphene type of two-dimensional structures, then carbon nanotube types of these one-dimensional structures, and buckyball, carbon buckyball type of this zero-dimensional structures, and the bulk unit cell kind of structures. These are the four basically main building block of the materials. So these materials informations basically we put inside the computers, and some processing will be going on inside the computers, and we will be getting some numbers at in the output. So basically in your hands-on session, you will be discussing about the first part where you make your input file, give the structure information, that is parameters, atom position, etc. And you will be finding out output some numbers, some that is constant, for example, some cohesive energy and some other properties, total energy, etc. And you will be analyzing these numbers. So first and third part you are basically doing in the that particular hands-on session. The important thing is the middle part, which is missing right now currently. So I am currently for today going to focus on this middle part, that when the structure goes inside the computer, what are the equations, what is the theory which is basically processed inside the computer, so that you get some number to analyze at in the output. Okay, so basically today I am going to focus on the middle part only. So if you see this structure, this particular cartoon middle part, we have H psi equal to E psi. So basically Schrodinger-like equations we will be solving inside the computers, and what are the historical development of these Schrodinger-like equations, and how these are developed to the many body equations. So I'm going to start to discuss about that. Okay, so if you see the description of quantum antibody system, so first part, so when you want to study any materials properties, any quantum system, so first thing is that how to describe this particular quantum antibody system. So you know that basically quantum antibody system is made up of the atoms and molecules. Okay, these atoms molecules basically these constituent the materials or the solids. Okay, and within that atoms and molecule we will have electrons, okay, and nuclei. If you see this picture, so we have this bigger circle, blue circle, these are basically the nuclei, and the small circles, these are basically the electrons. Okay, so these electrons are actually revolving around the nuclei, and nuclei are also considered to be moving in the real many body physical system. Okay, and we want to model that particular system. So this can be done by writing the equation. So first thing is that you have to write the Hamiltonian for that particular real physical systems of atoms, you can say molecules, or you can say nuclei and electrons. Okay, so the Hamiltonian consists of the 5 different energy terms actually. So you know the Hamiltonian is nothing but this is just kind of just the combination of the different energies, right? Hamiltonian, it has the basically 5 different energy part in that particular many-body Hamiltonian. First part is the actually the kinetic energy of the electrons. These electrons, small circles. This is the kinetic energy of these electrons, right? Second one is the kinetic energy of the nuclei, the bigger circles. Okay, the second part is the kinetic energy of nuclei. The third part is actually the electron-electron interaction. So these electrons, these are also interacting with each other. So this is the basically electron-electron interaction energy, which is the third part. Okay, fourth part is actually electron-nuclear interactions. So electrons will be also interacting with nuclei. So this interaction between the electron and nuclei, this will be the fourth part. Okay, so fifth part is the nuclei-nuclear interactions. These nuclei are also interacting with each other. So this particular term is given by the fifth part of that particular Hamiltonian equation. Okay, so these are the 5 different terms which constitute the many-body system. Okay, that is basically a real physical system of solids and materials, you can say. Okay, first thing is that we have to write the Hamiltonian for that particular system. Okay, so once you write the Hamiltonian, the next thing is that you have to solve this Hamiltonian. How to solve this Hamiltonian? As such, we cannot solve this Hamiltonian because it is very, very cumbersome. Directly, it is very, very difficult to solve that particular Hamiltonian. Okay, so what we do, we apply some kind of approximation. So what are these approximation? If you see the M alpha, second part here, M alpha is basically the mass of the nuclei. Okay, capital M alpha. M is the mass of electron. If you see the ratio of the mass of the nuclei and mass of the electron, it is very, very large. Means mass of the nuclei is very, very large as compared to electron. Or in other words, what you can say, that the speed of the electron is very, very high as compared to nucleus. Okay, it means that nuclei are much slower than the electrons. Okay, and if you calculate the Fermi velocity of the electron, it is actually 10 to power 8 centimeter per second. On the other hand, the Fermi velocity of the nucleus, it is 10 to power 5 centimeter per second. If you see the difference in the order in the velocity or speed, you can say it is 10 to power 3 order of difference in the speed of the electron and nuclei. Okay, so from here we can induce some approximation in the to solve this particular Hamiltonian. So that approximation is basically called the Born-Oppenheimer approximation. So this approximation basically decouple the motion of electrons and nuclei because there is a huge difference in the speed of nuclei and electrons. So we can decouple the motion of electrons and nuclei. So let us assume the fixed position of nuclei, and we assume that nuclei are much, much slower than the electrons, or you can say these nuclei are stationary as compared, nearly stationary as compared to the electrons. Okay, so what we do basically, we assume the fixed position of nuclei and we solve for electronic equations only. If you see this cartoon, so we have now bigger circle which are not moving now, not moving, they are stationary. Okay, and electrons are only moving around these nuclei, right? And the nuclei, what we can do, nuclei can be classically displaced. Okay, in the real physical system, it is not like that they are entirely stationary. So they are basically also moving, but their speed is very, very small as compared to electrons. So what we can do, we can move these nuclei classically by creating the potential in the field of electrons, right? So what we write now, we write the electrons Hamiltonian first. Electronic Hamiltonian, we have this one. Okay, so two parts are basically from removed from for the time being from here. We have only electronic Hamiltonian here. Electronic Hamiltonian is like first part is now electron that kinetic energy of the electron. Second is the electron-electron interaction energy. Third part is electron nuclei interaction energy, which is represented as a external potential. That external potential is nothing but this is basically the potential due to the you can say the on the electrons due to nuclei. It is external because these when the strength of this potential is basically be controlled by the nuclei. So that's why it is called external potential. Okay, so this is like H psi and H psi equal E psi kind of equation that has to be solved. And nuclear equation is like finding the energy of nuclei and the that nuclear interaction, you can say the energy. So this can be basically represented by the classical displacement. Okay, you can calculate the classical force on that particular nuclei in the field of electrons. That is basically change in the electronic energy with respect to the change in the or can say displacement in the nuclei. So what is the change in the electronic energy when you displace the nuclei? That is given. You can find out the force on the nuclei. That force can be actually added later on in the whole this energy term basically. Okay, so that's in this way we can basically do the all these bifurcation of the electrons and nuclei, and later on we can add these different interactions at the end. Okay, so we have only now electronic Hamiltonians. Now we have only three terms. We have to solve this particular electronic Hamiltonian, but still, many body problem of electronic Hamiltonian is not tractable because we are dealing with the many body Hamiltonian. So electrons are basically moving all the direction X, Y, Z direction. So there are basically various kind of degree of freedoms which we have to taken care. Okay, so that is still basically not tractable. So here is some approximation again. We have to apply this approximation. So first is like independent particle model. What this independent particle model says that if you see this particular cartoon, so we have electrons moving around the nuclei, which are fixed. So what this independent particle model says that these electrons basically, each electrons are moving in the average field of other electrons and the average field of the nuclei. So if you see this shaded blue region, this is the average field of electrons, and the blue circles, these are basically fixed position of nuclei. So each electron is basically moving in the mean field of electrons, other electrons and nuclei. Okay, so in this way we can approximate this particular Hamiltonian, you can say. So at a time we will take one electron from the sea of the thousands and lakhs of electrons in the many body Hamiltonian, right? So we can take one electron at a time, which we say that each electron is moving in the mean field of the average other electrons and the nuclei. Okay, so now many body problem reduced to a problem of independent particles. Now we are dealing with the each particle at a time separately. Okay, that is done by the independent particle model. So first, you can say independent particle model, which came into picture was the Hartree and Hartree-Fock model basically. Hartree method, Hartree approximation was very simple approximation. If you see this particular equation, this is the Hartree equation. So we have three terms here. First is called the kinetic energy part. Second is the external energy, which is nothing but interaction energy between the electron and nuclei. UH is the Hartree energy. This is basically simple direct interaction between the two electron charge distribution. Okay, so this is very crude approximation. Basically, what this approximation says that total energy of the many electron system is sum of the energy of the individual electron. If you calculate the energy of the individual electron, okay, so if you add these energies, okay, you will find out the total energy. Very simple approximation. And wave function, total wave function, was considered to be product of the wave function of the each and individual electrons. Okay, this was very crude approximation. It's not basically accurate, basically not accurate. Okay, so if you calculate the energy of hydrogen atom using this approximation, it comes out to be minus 13.6 eV, which is exactly what is the energy of hydrogen atom. So this is because in hydrogen atom we have one electron, so it is understandable that for one electron system, it is applicable, means Hartree approximation. It can be applied directly. So it give you the good energy, which is exactly to the experimental energy. Okay, but when you go from one electron to two electron, okay, then problem came into picture, right? So problem in the Hartree approximation is that Hartree method doesn't follow the basic anti-symmetric principles. Okay, it doesn't account the exchange and correlation energies which are coming from the n electron nature of the actual system. Basically, quantum many body effects were not included in the Hartree approximation. Okay, then this approximation Hartree model, it was further modified by Fogg and Hartree, which were basically the teacher and student actually. Okay, so what they did, that they said that the true n-electron wave function can be approximated as a linear combination of non-interacting one-electron wave function in the form of Slater determinant. Okay, so Slater determinant is like this. So if you want to write the Slater determinants for two-electron system, psi R1 R2, this can be written like this: psi 1 R1, that is the wave function for first electron, which is positioned at R1. Psi 2 is the wave function for second electron, which is positioned at R1. Okay, psi 1 R2 is the wave function for first electron, which is positioned at R2. And psi 2 is the wave function for second electron residing or positioned at R2. So this is how we can write the the two electron Slater determinant. Okay, 1 by under root 2 is basically normalizing factor. So when you solve this determinant, it can be like cross product by cross producting, it can be written like this. So two electron wave function is psi 1 R1 psi 2 R2 minus psi 2 R1 psi 1 R2. This is the two electron wave function. Okay, here all the quantum mechanical principles are included in the that particular determinant. Okay, if you want to include the spin in the that particular the Hamilton, that particular you can say set determinant, you can include spin like up spin, down spin like this, include these signs here. Okay, and if you calculate the total energy using the Hartree-Fock method, total energy for two electron system is coming out to be like this, minus 77.5 eV. So total energy in the Hartree-Fock system is sum of the energy of kinetic energy, external energy is electron nuclear interaction energy basically. Hartree energy is the simple two electron distribution interaction. Exchange energy, which came into picture in simple form, it is like interaction energy between the two electrons having same spin. Okay, so you are including spin in the that particular theory. So what is the interaction energy between the two electrons having same spin? This is called exchange energy. So when you calculate this for the helium atom, helium and basically atom, you can say this is the simplest many-body system, two electron system, simplest many-body system. Its energy was calculated to be minus 77.5 eV using the Hartree-Fock method. It is close to experimental value, you can say. It is close to minus 78.98 eV. Still, it is not that much accurate, that much close. That might be reason because we are missing something also here. That missing part is that correlation part. Correlation part is basically the, you can say in a simple way, that the interaction energy between the two electrons having different spins. So there is also two electrons having different spins can be also interacting. Okay, this part was not included in the Hartree-Fock theory. That might be the reason that that particular theory is not giving accurate or most accurate, you can say close to experimental value. Okay, so here comes the density functional theory. So where all the exchange energy and coalition energy were included in the basically this theory. So basically what is here is here is a transition from wave function to electron density. So Hartree-Fock theory are basically based on wave function, whereas density function theory is based on the electron density. So what is the difference? If you see that many electron wave function is written like this: psi is function of x1, x2, xn, different position of the electrons. Okay, so you can write this h psi equal to e psi. Okay, it contains huge amount of information, no doubt, but there is 3n degree of freedom for n electrons. For example, if you are dealing with the 100 electrons, there will be 300 degree of freedom, which you have to be taken care. That is very, very cumbersome, very, very difficult task to do that. Okay, so on the other hand, density function theory, there is only one variable, which is called density. All the properties of the systems can be considered as a unique functional of ground state density, right? Unique functional. What is this functional? I will discuss that part later on. So only one equations of density is remarkably simpler than full many-body Schrodinger-like equation. Okay, a special role can be assigned to the density of the particles in the ground state of the quantum many-body system. Okay, so let us try to discuss about this density-based theory. Okay, so if you see this density functional theory, if you see this title, density functional theory, which is the heart of all the many-body computational codes, okay? So there are basically these three parts, right? So density, then second is the functional, third is the theory. Okay, let's try to bifurcate these three different parts. Let us try to discuss first density. What is density? What is the functional? What is the theory? Okay, what is density basically? Okay, so density, if you see the simplest, let us take the electron density of the silicon atom. Okay, if you see this particular cartoon, is a density versus r distance. So here we can see this first peak, second peak, then there are this particular flat kind of shape of the electron density. These are core electron basically. So we have 1s, or if you see the silicon atom, electronic configuration is like 1s2, 2s2, and some 2p electrons there. Okay, so 1s and 2s, these are basically core shells. These are sharply peaked, and these are core electrons. Whereas the valence electrons, these are outermost electrons. They are diffused kind of objects are there. They are not sharply peaked. They are flat in nature. Electron density like flat in nature. Okay, so if you calculate the density, integrate the density, okay, of this silicon atom. So if you integrate this, what you will get? You will get the total number of electrons available in the silicon atom. Okay, total number of electrons available in the silicon atom. Okay, so this is how we can basically represent the density of a single atom, right? So electron density in DFT, in density functional theory, how you write density in the electron and the density functional theory. So this rho r density is basically written like this: summation over all the occupied orbitals. Okay, all the occupied orbitals. So we are dealing here with in the context of orbitals. These orbitals are like 1s2, 2s2, 2p orbitals in the case of silicon. So all the occupied orbitals, okay, it's square basically. So it is kind of like psi star psi kind of thing. Summation is there. Okay, so summation over all the occupied orbitals, phi I r square. This is kind of phi I star phi I, complex conjugate of the wave function, and multiply by a simple wave function. That will give you the basically probability density. You know that, right? So 2 is here because each orbital can contain 2 electrons, right? So 2 times of this particular summation over all the occupied electronic states, orbital states, right? So this is how we can just generate the electron density for a atom in the density functional theory. Okay, so if we know the atomic electron density, we can roughly generate the electronic density for solid, which is made up of atoms, right? If you know the density of atoms, we can roughly generate the electron density for basically for the solid. If you see this particular cartoon, this is the isosurface of the electron density silicon bulk diamond structure. You can see unit cell of that particular diamond structure. So atom, once you know the atomic density, so isosurface for the that diamond structure of silicon bulk unit cell can be roughly generated. Okay, this is how electron density in the density functional theory can be actually the obtained or generated. Okay, the second part in the density functional theory is functional. Okay, so what is that? Functional? It is not simple. It is like slightly tricky. So if you know the function is simple. Function is like mapping from a number to number. So your input is going to be number, your output is going to be number. For example, f is the function of x. X squared plus 1 is the function of x, right? So your input is number. So what you do, you put x is equal to 0, 1, 2, 3, 4, so on. And what you get in output, you get the number. So input is number, output is number. This is a mapping from the number to number function, right? What is functional? Functional is basically mapping from a function to number. So your input is going to be function and your output is going to be number, right? Now, what is your input? Input is function. Input is your fx, which is x squared plus 1. Input is function and output is going to be number. For example, x squared plus 1 is function. If you integrate this function with this limit minus 1 to 1, what you get at the output? Number, right? So your input is function, output is number. Functional is basically mapping from function to a number. So this functional is basically represented by the square bracket, whereas function is represented by this small brackets, right? So area under the curve is the simplest example of functional. If you calculate the area, if you draw a curve, you find out the area under that curve. What is this? This is the simplest example of the functional. Okay, now functional derivative. derivative of a functional with function, right? This is represented by f dash, this square bracket fx. This is basically the derivative of a functional with function. For example, delta of f of fx upon curly fx. This is simple. Okay, derivative of a functional with function. Okay, so if you see the example in the context of density functional theory, external energy functional is written like this. External energy functional is given by the integration of the external energy potential, external potential multiplied by the density. Okay, so you can represent like this. External potential is basically external potential. External potential as a function of density is given by change in the external energy functional with respect to change in the density. So change in the basically that particular functional with respect to function. That is the simplest example of the in the context of the density functional theory. Okay. Okay. So density functional, that external energy functional, change in external energy functional with respect to that function. This is given. This will give you the external potential as a functional of density, right? That was the functional. Okay. Third part is the theory. So what is the theory in the density functional theory? So theory of that density functional based theory is basically based on two fundamental theorems. Okay, these fundamental theorems are called Owenberg-Cohen theorem. These are called Owenberg-Cohen theorems. Okay, so there are two fundamental theorems given by Owenberg and Cohen in 1964. First theorem says that there is a unique external potential determined by the ground state electron density that exists for each and every quantum mechanical system. Okay, so it says that for every quantum mechanical system, every quantum mechanical physical system, there exists a unique external potential, which is determined by the ground state electron density. Okay, so this particular theory basically it gives the existence of the density functional for a given real physical system. This gives the existence of the density functional. Okay, second theorem says that that particular total energy of the system can be represented as a functional of the density, which is granted by the first theorem. Okay, so basically second theorem basically write the total energy of that particular quantum mechanical system in terms of the density functional, which is granted by first theorem, right? So total energy of this ground state energy as a function of density is given by f of rho r. F of rho r is basically the universal functional. It says first term says that every system there is a universal functional available, right? Plus external energy functional, okay, which is basically electron nuclear interaction energy part. Okay, so it says that if you write the ground state energy as a functional of density, which is sum of the universal functional energy of the universal functional and external energy, it is always going to be greater than equal to the true ground state energy. That is nothing but that is the variational theorem, variational principle. It says that when you guess some wave function, some density of a given system, and you calculate the total energy using that guessed guessed wave function or density, your total energy you are calculating is always going to be greater than equal to the true ground state energy. That is the simple variational principle basically, which is basically applied here to minimize the total ground state energy of the system, right? That was the two fundamental theorem. Around this density functional theory will be revolving, right? So these were the density functional theory basic definitions. Now comes to the Cohen-Sham formulation. Basically, these theorems and these fundamental definition, these are only the bookish definition. Okay, there is nothing that how we can practically implement these things in the basically in the real for real system. Okay, so these theorems are fundamental and bookish, or you can say the statements only. This doesn't apply this theory particularly for the actual practical way, basically. So here comes the Cohen-Sham formulation. In 1965, Walter Cohen and Sham, they have given a practical formulation that how can we implement that theory practically on the computer. Okay, so what basically Cohen and Sham did, they decomposed Cohen-Sham basically n electron energy into n electron energy into n1 electron energy. So what was that? If you see this particular cartoon, this is actual system, Hartree-Fock kind of interacting system. Kinetic energy is interacting. Okay, external energy is the non-interacting because we are taking actually one electron at a time and trying to find out the that interaction of that electron with the nuclei. Okay, that's why it is non-interacting. Hartree energy is the interaction between electrons and electrons. This is also basically interacting energy. Exchange energy is the interaction energy between the two electrons having same spin. Right? This is a actual interacting Hartree-Fock system. So what Cohen-Sham did, Cohen-Sham did, they decomposed this kinetic energy into two parts: kinetic energy non-interacting and kinetic energy interacting. Right? Kinetic energy non-interacting means they are taking one electron at a time from the each orbitals, occupied orbitals. Okay, non-interacting part is coming into picture because in the single orbital state, two electrons can reside. One with upspin, other one will be downspin. So interaction energy between two, okay, kinetic motion. So I am discussing here what is the interaction energy during the kinetic motion of these electrons. This is the non-interacting kinetic energy. So that part has been basically bifurcated here in the kinetic energy part. External energy was the non-interacting. Hartree energy is basically interacting electron-electron interaction energy, and exchange energy and correlation energy. Here, correlation energy was included because two electrons having different spin also interact with each other. That part has been included here. That was the interacting part, right? So that was energy decomposition in the case of that Cohen-Sham formulation. So what was the output? What they found at the end? Non-interacting one electron system. So it was like kinetic energy is now non-interacting. The kinetic part, that the interacting part of the kinetic energy was included in the that exchange and correlation part that was interacting. Okay, so kinetic energy, the interacting part was included in the exchange and correlation energy part. Okay, so now it is here the kinetic energy non-interacting, external energy non-interacting. Hartree energy was considered now non-interacting because now we are dealing in the mean field. We are taking one electron at a time from the sea of, for example, thousand of electrons. We are taking one electron at a time, and we are calculating the average interaction of that one electron with the other electrons distribution. Right. So now it become the non-interacting system. Okay, one electron at a time. So it is now non-interacting system. Right. So this is the exchange correlation part is now clubbed together. Where exchange part, correlation part, and kinetic energy interacting part has been added together here in the to make this exchange correlation and which is interacting now. So in this non-interacting part, so we have now only this part which is in the energy decomposition. Exchange correlation energy is only the non-interacting. All energy terms now become the sorry, exchange correlation energy is the interacting part. All other energy terms become the non-interacting, right? So that is the decomposition of the energy given by the Walter Cohen and Sham in 1965. So what they did basically, they have transition from n electron system to the one electron system. So if you see this cartoon, n electron system is interacting system, actual system is interacting system. This can be represented by, you can see these men, they are holding hand with each other. They are looking also to each other. They can interact with by their eyes to each other. Okay, they are strongly holding hand with each other. So in principle, you can calculate the kinetic energy of this system, and the U is the potential energy. You can calculate exact density or exact energy in principle. Okay, whereas in the one electron system, which is non-interacting, what was done basically, if you see physically, what was done, real human beings have been replaced by the robots. If you see, these are robots, these are real human beings. Okay, these robots cannot interact with each other. They are not holding hand with each other. Okay, they are not interacting with their eyes to each other. They are only looking forward. Each of the robots are looking forward, not interacting with each other. But there is a one thing which make them interacting is the exchange correlation energy part. That exchange correlation energy basically that is interacting still. That is still interacting. Okay. So in principle, we can calculate the kinetic energy non-interacting. We can calculate the U effective potential energy part, and in principle, exact density and exact energy can be in principle obtained. So this is how we go from n electron system, n electron many-body system to the one electron system. To the one electron system. So one electron system solution is easy as compared to the n electron system, right? So we have to now solve single equations. Okay, so if we have 100 electrons, we will have 100 simultaneous equations. These can be solved by taking like Hamiltonian matrix and diagonalizing the matrix. That is how we can easily done that particular thing on the computer. Diagonalization of matrix can be done on the computer easily. Okay, so how much time I have? Professor Singh, how much?
Sir, 15 minutes.
15 minutes. Okay, thank you. Okay. So if you see the energy decomposition in the case of simplest many-body system, that is helium. Okay. If you see here, 53% is the external energy. Okay. 16% is the Hartree energy, and 22% is the kinetic energy. And exchange correlation energy, which is which is interacting basically, and which is also unknown, it is only 8.38%. It is very small. If you see the total energy of the many-body system, exchange correlation energy part is very, very small, 8%. Mainly it is constituted by this energy constituted by the electron nuclear interaction. Okay. If you see this particular cartoon, energy versus interatomic distance of two helium atoms to make a helium molecule. If you see this cartoon, so this is exact energy of the helium molecule here, exact energy. Hartree-Fock energy somewhere here, Hartree-Fock energy. Hartree energy is quite off somewhere here. If you see density functional theory, it's very close. It is very close to exact energy. It is very close to exact energy. The density functional theory gives the very good approximation to the total energy of the many-body system, you can say. Okay. So if you see this particular composition, so Hartree for that particular exchange correlation energy is very, very small contribution. So why we bother of such a small exchange correlation energy? If it is so small, why we bother of that small energy? Because exchange correlation energy is very, very important. It is actively involved in the small changes which is happening at the atomic level. Okay, at atomic level, what are the small changes happening? That is influenced by the exchange correlation energy. That is why it is important. It is also very crucial to determine material properties such as bonding, spin polarization, band gap formation. It plays very, very important role. That's why we have to focus on that particular exchange correlation energy part. Okay, so that part, how can we approximate that exchange correlation energy part? So we have to discuss that. So before that, how can we solve that Gromsham equations? This can be solved by using the variation principle with constraint minimization. So we have to include here Lagrange multiplier, because here total number of electrons are fixed. These are not varying. If you are dealing with 100 electrons, they will remain 100 when you minimize the energy. It cannot go like 99, 105 or so. It is fixed. So if you have learned the classical mechanics, there is a procedure, constraint minimization, which is called the Lagrange multiplier method. Okay, so this particular things can be done using the Lagrange multiplier method, because here number of particles are fixed. Okay, lambdas are basically here the Lagrange multiplier. So variation principle, change in energy, you can just find out the respective orbitals. Okay, which is equal to 0. That is a variation principle. To minimize energy, energy can be written like this. So what you do basically, you rearrange this particular equation and put the different energy functional here. That is external energy functional, okay, Hartree energy functional, and exchange correlation energy functional here you put here. Okay, and these lambda i's which were the Lagrange multiplier, okay, that lambda i's has been placed to that epsilon I at the end. So what is this now? This is basically the Gromsham equations after putting these different energy functional. This is first part is the kinetic energy part. Second part is the effective potential, and epsilon I, which were basically lambda i's. Lambda i's were the Lagrange multipliers in that variation principle minimization procedure. Okay, these epsilon i's are basically now energy eigenvalue, and this particular equation is called Gromsham equations, HKS H psi equal to E psi kind of equations. Okay, and these epsilon i's are basically, these are represented like this change in the energy with respect to change in the density that is equivalent to chemical potential, and highest occupied state is equivalent to exact ionization potential. Okay, the epsilon i's are basically in terms of chemical potential, the highest occupied state in that particular electronic system in the alters state, this is equivalent to the exact ionization potential. Okay, so this is how we can mathematically represent these equations. Okay, now coming all the part of this particular equation, like external energy part, heart energy part can be find out easily, and the exchange correlation energy part is still difficult to find out. For this, there are different approximations. So I am not going to discuss about this particular exchange correlation whole part. I'm directly coming on the theory part. So what is the theory to basically represent this particular exchange correlation part? This is given by the local density approximation or generalized gradient approximation. So if you see what is this approximation actually, assuming the varying electron density such electrons to see the entire landscape in the same way as they see locally. So see, actual picture to solve the many body Hamiltonian many body system is like this. This is actual picture. Actual density impossible to calculate the exchange correlation energy. So actual density, it is very impossible. It is very impossible to find out its actual density and to calculate the exchange correlation part. Okay, so what you do in local density approximation, we bifurcate this actual density homogeneous electron gas basically. Okay, this particular that particular density in terms of the homogeneous electron gas. If you see this, so we have bifurcated these particular actual density in these small boxes. So what this local density approximation says that this local density approximation means density is locally constant. If you see the small box, density is constant. Density is second box, constant. Although this density may be small, slightly different in the different boxes, but in the same box, it is basically constant. So this can be done by taking the ideal uniform electron gas, ideal density for uniform electron gas. You represent that particular real physical system using the uniform electron gas or homogeneous electron gas and bifurcate the small boxes here and we says that electron density is locally constant, and then we calculate the exchange correlation energy. Okay, so when you calculate exchange correlation energy, pictorially, you obtain this picture using the local density approximation or generalized gradient approximation. Okay, so this picture is basically it is capturing the actual density. If you see this first picture, it is capturing the features, not exact, but its features are captured by the local density or the generalized gradient density approximation. Okay, so this is basically the real physical interpretation of the local density approximation. Okay, so local density approximation functional can be obtained by integrating the exchange correlation energy for homogeneous electron gas multiplied with the total density, right? So exchange correlation energy, the potential, okay, in terms of local density approximation, nothing but this is the functional derivative of exchange correlation energy with respect to density, right? This is the functional derivative of the that exchange correlation energy local density approximation with respect to density. Okay, but actually what happened? So GG approximation, which is more accurate, because we are saying that this density is locally constant, but for real physical system, density will be varying with distance. It is not actually locally constant. So GGA, basically generalized gradient approximation, it captures both the local and semi-local information. Okay, what is how it can be done with the help of this equation? So this exchange correlation energy in GGA, it is given by integration with respect to total density. Exchange correlation energy in the GG approximation is functional of density as well as gradient. What's the meaning of that? So we have included density as well as gradient, mean direction. Okay, we have also included the direction and the density, means in the what direction, in the particular direction, what is the density. So gradient of density has been included. That is basically the most accurate way to do the DFT calculations using the generalized gradient approximations. Okay, so GGA kind of approximation you must have done in the that hands-on session, GGA functional, LDA functional, right? So hybrid functional part, I'm skipping this part. This is slightly tricky. So only GG and LDA part is I am discussing here, right? Now, so once you know all the energy terms, like kinetic energy term you can easily find out. Second is the Hartree energy. This can be easily find out. This is basically the double integration between the two charge distribution. Mathematically, it can easily find out. Third is the external energy part. External energy part can be find out using the pseudo potential. I'm not covering that part here, pseudo potential part. So maybe in the hands-on session, this can be discussed. Pseudo potential part that constitute the third that external energy part basically. Fourth part was this exchange correlation part, which is covered by the local density approximation or the generalized gain approximation, right? So how can we practically done on the computer? So first thing is that we find out the trial density. That trial density can be obtained from the it will depend upon the system, which system you are basically finding out or studying. For example, you are studying the silicon system, silicon atom. So you take the electronic configuration of the silicon, right? And using these electronic configurations, you write the density rho, and this can be written like summation over all the occupied orbitals as we discussed in the previous slides. So once you obtain density, an exchange correlation part functional from this that local density approximation or GG approximation. So once you put these inside the equation, you evaluate basically the Cohen-Sham Hamiltonian. Okay, so once you define trial density exchange correlation part, okay, you find out you put the different energy functional in the Cohen-Sham Hamiltonian. So once you put this Cohen-Sham Hamiltonian, these different functional part in the Cohen-Sham Hamiltonian, you evaluate this Cohen-Sham Hamiltonian. That is, you then find out to solve the Cohen-Sham equation like H psi equal E psi. Simple Schrodinger-like equations. So when you solve H psi equal E psi, you know that when you solve the equation H psi equal E psi, what is the solution? Solution is like psi. Okay, so here we will have phi's. So see, these are new phi's, new orbital states. You have started with some trial orbital states. You are getting new orbital states, or from new orbital states, you are getting new density. So from the old density and new density, you can compare that how accurate, how close is your new density as compared to old density. If it is very close as compared to, you can put some tolerance factor there in the computation in the computer. If this is satisfying the tolerance criteria, then it is considered to be converged. This density is considered to be converged, and then you can calculate the forces on the atoms and you can update the ions positions. But if this density is not converged, what you do, you put some portion of that density back to that Hamiltonian to evaluate that different potential part in that particular Hamiltonian. Then again, repeat that same procedure. This procedure, this is internal procedure. If you solve these DFT on the computer, you will see some energy convergence. Internal loop will be there. This is called electronic minimization. This is basically minimization of density, electron density. Okay. Second loop will be the once you have converged density, then what you do means you want to optimize the whole system. You want to relax for example, silicon bulk system or some other molecules or atoms, right? So what you do, you just update the atomization. Means initial precision was like 0.1 angstrom. You update like 0.12 angstrom. When you update the precision, same. Firstly, this internal convergence will be there for density. Then outermost part, that outermost, you can say the loop will be for the ion relaxation. So this is called basically the relaxation loop. Outermost loop is relaxation loop, and in the innermost loop will be the electronic minimization. For each of the relaxation loop, there will be various internal electronic loads. So for one, you see output file. So for one or each of the ion position updation, there will be internal electronic convergence, right? So once you obtain this atom, the lowest energy position for atoms and molecules, then you will say it is converged. If it is not, then again this can be done, and you can repeat this procedure again and again until you get the converged forces on the atoms or under consideration. Okay, so once you get converged forces and energy, you can calculate the energy and other properties. Okay, so once the total energy of system is obtained, example in terms of lattice parameters, various fundamental properties comes out naturally, like stable structure, bond lengths, angles, cohesive energies from energy minima, bulk modulus, elastic constant, etc. All the various kind of structures, various kind of parameter can be easily found out. So first fundamental things in density model theory is that you have to find out the converged energy, total energy basically. Okay, for example, bulk modulus is the double derivative energy with respect to volume. Pressure is the energy derivative energy with respect to volume. Force is energy with respect to position. And this elastic elastic constants are basically the change in the energy with respect to strain. Okay, so once you obtain this energy, basically total energy, converged total energy, automatically you can find out various kind of parameters, right? So, see, the development of this particular theory in 1998, Walter Cohen got Nobel Prize in 1998. So this theory was developed in the 1964 or 1965, but it took like you can say more than 25 years to get Nobel Prize for this particular theory. Reason was because during that time, 1965 or 70s, so the computer development was under progress. So the computer power was not that much there. So once we came into the 90s, computational power becomes slightly powerful. Computer becomes slightly powerful. Then this theory was basically actually implemented on the computer. Practically, we were able to basically obtain some kind of the energies which were comparable, you can say, compared with the actual experiments. So that was the basically reason that it took more than 25 years to get Nobel Prize to Walter Cohen for this development of this theory. That theory nowadays is basically a very important theory, which is basically used almost all the branches of science, not only physics, material science, chemistry, biology, and other simulations people's. This theory is basically used by the various branches in actually. Okay, so I think I should stop here for today. So that was the basic introduction to density functional theory and how it is basically important in the context of the numbers you are basically getting in the hands-on session as the output. So yeah, so any questions? I am ready to answer any questions.
Thank you, sir. Thank you for this wonderful presentation. I have been to many workshops, DFT calculations, but theory I could never understand. I mean, I could never understand. Today I understood this. So this
Thanks for
very full session.
thank you.
Functional, everything I understood today. Because many times we were doing only this using software Gaussian and Gauss view, and we are doing calculations. But theory today, I mean, I had attended many, but I was not able to understand those things.
Thank you for this.
Yes. Dear participants, we are open for questions.
So thank you very much for the nice talk, Dr. Ashok. I have one question that you skip the one part, that is the hybrid functional. Yeah.
Yes,
So
yes.
anyhow, we will check that by itself because it was interesting.
I can explain if you
and,
want. I can answer this question. So
yeah,
hybrid.
but
Yeah.
yes, but at the moment, I think so. If we don't have time for the discussion, we will contact you. I
Yeah,
will
you can
personally
contact me.
contact you
Definitely.
for the and if your PPTs are open to for the discussion, because you summarize everything very well. So you can share that with us,
Yeah, I
and
will share. I
so
will
that
share.
we can go through. Yeah,
Sure, I
thank
will
you very
share.
much. And I don't have, because I went through this several times, this the theory, and I really enjoy the talk. Yeah,
Okay,
thank
thank you.
you.
Thank you.
Any other participant? If you have any question, you can
Sir, I have got one general question to ask. Sir, first of all, I thank you, sir, for this wonderful presentation. I have learned many things from this talk. One question that came to my mind is that both Cohen and Sham, they have developed the theory, but why Cohen got the Nobel Prize? What is the reason behind it?
So I think Walter Cohen, that was senior most person. He was maybe that was the reason. I don't know, but yeah. So Walter Cohen and Sham was also involved there. He was, I think, his student. So Walter Cohen was senior most person. He was basically involved in the various kinds of the approximation, which is basically implemented later on. So he was from the starting from this theory, he was involved there. That might be the reason he got this particular thing.
Okay, sir. One more question regarding this plane wave DFT and the Gaussian that I am using right now.
Yeah.
Sir, from where this bifurcation take place means regarding the localized basis and the plane wave basis. If
Okay.
it
So
can be
yeah, so I
discussed.
have not discussed about, because generally in the DFT workshop, I gave the two talks, one for this particular thing, second for this later part like pseudo potential, basis sets and all. So, but basically basis sets are the things basically which will bifurcate the different codes. Okay, so what is this basis set? Basically, basis set is the basically representation of the wave function. So see, you have wave, we are dealing with the phi's. Phi's are nothing but these are basically wave functions. So when you implement the theory on the computer, okay, so we have to represent this wave function, and you cannot write like psi or phi's in the on the to give the computer. Computer doesn't know, doesn't understand what is psi, what is phi. Okay, so what has to be done? We have to basically represent these psi's or phi's in terms of the mathematical functions. And these mathematical functions are called basis sets. And these basis sets are various kinds. Like these basic, mostly used basis sets are like plane wave basis sets. So you represent psi in terms of the exponential factor e to power iota k dot r, right? So this will be representation of that particular wave function in terms of the that plane waves. Okay. Another is a Gaussian kind of function, like the Gaussian function e to power minus that xt or something like that. Okay, that so these are different representation of the wave function. Basically, different mathematical representation of the wave function. It will give rise to different basis sets. Hence, it will give rise to the different codes. For example, VAS has like plane wave basis sets. Gaussian has this Gaussian basis sets. Okay, so based on this, these basis sets are basically these codes are bifurcated. So Gaussian basis sets are also good, but most of the time chemistry people use this Gaussian basis sets. But physics people, if you are doing physics, periodic system, if you are dealing with periodic system, plane wave basis sets are considered to be most accurate. But siesta is the code which is very, very good code, very, very fast code. It gives reasonably very good result, although it has very unique kind of basis sets. It doesn't have any kind of Gaussian kind of basis set. It doesn't have like plane wave basis sets. It has numerical atomic orbitals like basis sets. It's a very different kind of basis sets. It is considered to be very, very good code actually. It is very, very good. I have personally used this particular code for 5 or 6 years initially in my initial stage of my research. So that was very good code. So this is very good. So yeah, so various kind of basis sets bifurcate the different codes actually. It will depends on your problem, which kind of problem you are doing, and which kind of course is good for your study. Depends on you.
Thank you, sir. One more question, sir, if you allow me. Sir, regarding this mixing parameter, the mixing of the densities or new density with the old density. So it is variable and it is in our hand. So how to use it judicially means how much mixing we will do.
That is a good question.
If you are
Let's start when you do this these calculations, convergence heavily dependent on that. Sometimes what happened is you also so you have to play with this basically mixing weight. So basically, what is this? So mixing weight is in density. Uh, it is like this. What is how much your new density is different from the old density, which is you have guessed basically. You guessed the density initially and get new density. How different is this new density from the initial densities? By default, in most of the codes, for example, in the I think in C star, it is 0.25. Means it will feedback that particular density 25%. It is not like that we cannot basically feedback all the new density to the input to calculate again this whole potential terms. It is 25% by default in the siesta, I think. Okay, but if you are not converging, if this density is not converging, means 25 is good, 25% is good. If you see that some system it is not converging, you have to reduce it. You have to reduce it, like go to the 10%, go to 5%, go to 1%. Although your number of steps will be increased, your time will it will take more time, but it is definitely that your system will be converging. So you can reduce this mixing parameter that 0.25. You can go up to 0.1, 0.05. Definitely your number of tests will be increasing, but you definitely get some converged density at the end.
Thank you, sir.
I think so in the siesta FDF file, it's called mixing weight parameter. Yeah, that we usually take it 20% or 25%.
25%, yes, by default.
Yes, sir. Thank you, sir, for this wonderful session, sir.
Nice presentation, Dr. Ashok. Good.
Yes, sir. Thank you,
Thank
sir.
you, thank you.
So, dear participants, we'll break for 10 minutes. Then we'll come back for the hands-on practice session given by Dr. Mohanlal Verma, sir. 10 minutes break, then we'll come back.
Yeah, let's meet after 10 minutes. Okay, thank you.
So in this hands-on session, we are going to design materials. And before that, first I would like to thank everyone for learning from this FDP, because your interest actually encourages us to develop some new materials and new tutorials to help you. So today, first, whatever we have covered so far is we have installed all the tools, and also we know how that APF file works, and Dr. Imran and Sajal helped a lot to understand all the things. So before starting that designing part, first of all we should check our system, whatever the system we are using, that is the laptop, desktop, whether in Ubuntu directly completely installed that window based services like the virtual box and AWS. So first of all, let us check all the tools properly installed or not, and how we can verify that. So first, installation process was related to system. And, for that, we have a single command. If we are using this command, that is system, and it's working properly. So this type of text will appear on your screen, and this is the command for the serial mode, and we are using only one processor. And as I mentioned that in your system you can check about the number of processors. This is the configuration of my laptop, that is here I'm using this 8 processors, so I can use out of 8 processor at least 6 I can use. And, the frequency of each processor is 2.8 GB. That SSD I'm using 512. These are the processors. Ubuntu 22.04 I'm using this. So if I want to check that how many nodes it is shown by each tool. So another command is there. So let me come out 5%. Before that, I can just take a screenshot by using create screen here and pasting to this. So this is that verification of your this is for the series one. For parallel, by pressing Control C, we will come out and yes, these are the files. And then for parallel, I am using MPI run. MPI, this is message processing interface. So MPI run with the system. So change is observed here. Everything, other things will be identical, but here the running on 4 nodes in parallel, it is clearly mentioned here. So you can compare this to the previous one. So these are the verification that Sista is parallelly installed in my laptop properly, and by using that script we have shared you, by using that, and if it is run errorlessly, then this type of message will be there, and you can say that it's version of 5.4.0. Somewhere it's version mentioned. Although this is unreleased version, as per that the message comes, but it's a good one. So this version is installed on your system, I think so. Anyway, so this is the verification of that installation of this system. Second, we tried to install several visualization and pre and post processing utilities tools in one of the sessions, and we can check one by one that the installation of all those things. So that ZDIS, this is one tool, and when you press this type of window will appear, and here in this case you can go through this. All these are that similar to that our some tools related to our Windows system. So this is open, save, close, import, export, edit. We can copy, paste, color. We can change that. Tools we can visualize. We can create and other things. We can do. So at least one should have the interest to go through this utility and click every point and try to get what actually happening after clicking that one. So this is what tool, and if you are to uh, they know the capability of this tool, then you can go through its web page, that is ZTIS web page. So let me type here ZTIS. So yeah, so this is that the web page. So here security reason it's not opening. Anyway, so you should try that. And also that the second one is the first one, and you can come out from this utility by clicking quit here or just press on the cross. And second is Vesta. So in my system, Vesta is also installed. So this is that utility, and for design purpose, we can use Vesta. And again, these are the same terms that edit, object, and utilities. Although this Vesta is very versatile tool, and people of different fields are using Vesta as a software. And next is X crystal. Let's try one by one X crystal. This is that X crystal window, and you have that open, and also you can check your plotting tool, that is grace. So we during that plotting tool we use grace command, but to open that we will use this X and grace. So that plotting tool is yes installed. So in order to verify that whether it is properly installed or not, you can use this. So it's yes running, working, and more utilities like JMO is also good to visualization and pre-processing utilities. So all these utilities are free of cost, and one can use this utilities. One more is the Dr. Okay. Please send your all the codes you will be first. Okay. So all these are that's okay. So these are that utilities we are using. So one by one, try all these commands on your system. I will hit 5 more minutes. Molden. So this is that view of the Molden. So time to time we are going to use all these utilities. So this is Molden, and obviously we are not opening anything. So the screen will be blank. Definitely that the background is taken blank. And in order to come out from this, we have to press here this skeleton. So these are the tools. So we have Extrusion, Molden, JMOL, XMGrace, Vista, GDIS. These are the tools, and we have installed this. And if you want to install this by a single click, then we have one script for this visualization tools also. And by using the single that the script, you can install that, and for that should be available here. Yeah, so this is for all the visualization tools, and also this is shared in my GitHub. So you can use this for if you still you missed the installation part. So today I am going to that. Please go to that video lecture shared by Dr. Gaurav in the channel, but you can go through this, and the method of running is simple. This is that script, so you have to just press sh and use this, and that will be installed automatically. So let me show you how you can use that. Although that and the process are taken from the same visualization script. So this is very small script, and this will create this will install GDIS, Grace, Expression, JMOL, Molden, Avogadro, and that this Wine also. If you want to use some window-based utilities in anyway, so we have these tools available with me, and I believe that this will be available with you also. And now let's begin that who is just Yeah, so this is these are the tools available with me, and now the first part is over that the verification of all the tools system and all that pre and post processing. Why I am saying pre and post processing, because some tools we are going to use before running system, and some tools we are going to use after processing system. So these are that tools, and some are common also where one can use as a pre as well as post processing. So these are the tools, and I believe that this has been installed properly. Then the second one is that the creation of that FD file. So yesterday that Dr. Ram has given a wonderful talk about different part of this FDF file. So let me open some sample FDF file. Yeah, so let me open it. So in spite of searching that, we can use this one. Yeah, so this is the input file for M and O, and basic components have discussed yesterday. Anyway, fine. So that the first part is that system name and system label. Second part, the number of atoms and the number of species, and these are the coordinates, and the key points, and also that the constant and exchange correlation function, basis sets, and other things. And the things have been explained in today's lecture by Dr. Ashok also. And I think now you are familiar with all these terms, and we are going to use all this in our FDF file. So I'm using this as a template. So, and how to create this FDF file, it is explained by Dr. Imran. So let me just give one overview on this again. So we will begin with some tools like materials project. So I'm opening this materials project. And then clicking here, and then this will start exploring, because this needs the registration also. And the registration is just you have to give your email, etc., and that will open. So you can open this material project, and this is that details of that database available, and how many registered users are here, materials are there. We must have the habit to explore such type of web page. So many good informations are given, and that this one dashboard is there, community is there, and that API and machine learning are being used by this, and we can explore any material by clicking here. So this is the periodic table of that. And so before starting the study of any material, one should go through this database and search about that one and check the details of that material. For example, I have a very familiar example of that SIC, because so on the basis of that SIC, there are some other components also in it. It's suggested by this particular utility that TIA2 SIC, but I need this SIC, so I just click here, and the details of this SIC it's mentioned here. With that, it's a crystal system and other things, and the cubic structure is here, and hexagonal is here, and that number of sites, number of atoms are showing here. And also for some other materials, for example, like yesterday JDN was taken as an example. So you can take gallium arsenide things. These are some familiar materials. So this is for the gallium arsenide, cubic, hexagon. So any of the materials you can take it. Just I'm downloading this hexagonal. So click here. So you can select any of the material. Yeah. So you can rotate and watch, observe its structure like this, and then download its CI. So the first step, if you are studying that crystalline structure of any material, so first you can search that material in similar database, and I have mentioned some other database also in my talk. So that that material project is one of the best ones. So that CIF file is here. So this will now will be downloaded in this, and I am creating here one folder for this gallium arsenide project. And then select. So here, by clicking here, I can directly go to that folder. So in this folder, this gallium arsenide CIF file is available. So you can download your own material similar to that, but as a example, if just we want to compare that whatever that study we are performing here, you should start with this gallium arsenide. So this is that gallium arsenide CI file. So the step number 1, we have to download that CIF file from material project. So in the second one, so first complete this, the first step, that download any CIF file, and then I will proceed the second step. So please download this, and if completed, mention in the group it's completed. Completed. Download the CIF file of gallium arsenide. Should I proceed? Okay, I think everyone has downloaded this gallium arsenide CIF file. The second step is we are converting this with that GDIS in FDF file. So step number 2, use this GDIS and gallium arsenide CIF file. So use this command and open this CIF file. So similar picture will appear. So this is that picture of gallium arsenide hexagonal structure, and we can observe this in different direction by having this view. So click here along x-axis, that is along x-axis. This will look like this. Along y-axis, this is look like this. And along z-axis, this will look like this. So in all direction, in all faces, you can observe this. This is xy plane. Y means this is xz plane, and x means this is yz plane. So this is xy plane, and after, yeah, even that ABC, the same thing is there. So ABC is here. These are that we are viewing in the different direction. Watch this and observe this in a different direction, and we can use this edit display content. So that content showing the total number of atoms, and this is working as a molecule here, and the total charge is 12 here instrument. Second, that editing, so you can sorry, this is you can display in the different models, ballistic and so. And then editing, so you can edit means you can change any elements here, and also you can add some atoms and other things. This is the editing part. Image, so you can just change the size. So one by one we will use the terms. The first part is this is the opening of the CIF file by using GDI. So I hope that everyone on everyone's screen this is appearing. So the second one, that is the third part, that is you can save this simply as PDF file. So this gallium arsenide model name is there. So this is just gallium arsenide, and that FDF is there. And also this utility is applicable for so many different tools, XYZ, XML, Sista, that is powder sale. So different file formats you can generate by using this utility. We are using Sista. Yes. So that gallium arsenide FDF, this is Sista, and let me save this. Now let us check this. So first to save that is FDF file, and let's observe that FDF file by double clicking on that. completed. So, but here one strange thing we are observing here is it is not the complete FDF file we have observed earlier. For example, and, I've shown you one FDF file. This is sending a file. That FDF file I have opened. Yeah, I mean, this was that FDF file. This was. So this is that FDF file where this we have this MNO. Number of atom is 4, okay, but number of species is showing 2 here. One is that Mn and second one is O. But in this gallium arsenide, which is actually generated by that GDIS, it is observing that there are 4 species. One is taken as gallium oxide, gallium 0, gallium 1, 2 and 4. So that is taken as 1, 2, 3, 4. So this is not the term we are directly going to use. So in order to convert this file into that our FDF file, either manually we have to modify this, or there is one more method to modify this is first to open this GDI, this is that open one. And in spite of saving this as FDF file, let me first save this as CIF. So open that CIF file first and save this in form of CIF itself. And yeah, yes. And then, so first open CIF file, save this in form of CIF file, and then we will open again this CIF file. This is the term, and now then we can save this as, this is whatever appearing right now. Let me save this again as a GIF file. Yeah. Now let us open that. So reload this. So this is that previous version of that FDF file, and now the new version of FDF file is this. So here, this is that gallium arsenide is there. Number of atom is 4. Number of species is 2. Gallium arsenide is here, and these are lattice vector and lattice point, and so many default parameters are added here. So here I am going to use one more, that is system name, that is gallium arsenide, because it's given in this one. So that system name and system level should be there. Only system level was mentioned, so just add system name. Other parameters are okay, but there are so many default parameters. So out of these parameters, we have to use some useful flags, useful lines. But how to decide this? So I have used some default lines in my FDF file. So I just copy these lines from my template and paste. So I'm sharing this template to you also, and prepare your FDF file similar to this. This gallium arsenide. So let me first share this template to you all. clicked the wrong one. Here that my template label is this. So I'm setting this template to you all, and the bottom part is that default part which we are going to use in this coursework and also in your sister run. And time to time we will add some extra flags, extra blocks to study different properties. So this is that the template for that API file. So what you have to do first to download that CIF file, open that with GDIS, and then next save this the same with that GDIS, and then again open that CIF file, and then create that FDF file by saving that and manipulate that FDF file. So this is that FDF file prepared by me, and now prepare yourself and report me. I'm waiting for 5 minutes. If you have completed that, then report me. So I shall proceed now. So this is the method of FDF file generation, and I have been I I've shared that FDF file as a template to you for your help. So what you have to do, you have to just download that CIF file and convert that in form of FDF file by using GDIS. But GDIS is giving so many extra lines in their FDF file generated. So what you have just to delete all extra lines after coordinates and paste the lines from my template, and then your file will be ready. And the top of that, you have to mention that the system name also. So this is that FDF file. Now the first system run yesterday. After run tried to run that system one. So for that we need this type of that FDF file, and also we must have the pseudo potential file corresponding to each elements. So how to download that pseudo potential file? Yesterday it was discussed. So and also that link was shared. So even that you can search using Google that gallium.psf pseudo potential. So that PSA file, this is the extension for the pseudo potential file of the system used by Sista. So these are that virtual world for the pseudo potential. And now we will search for the gallium. So here that lithium and that gallium is here. So many PSF files for the gallium is available. So out of these, we are going to download this for Sista. So this is that Sista. So here there are two files. One is for the semi-core, and second one that 3D with this. So any of that, I'm using this with 3D. So the assignment is you should use these both too, and check that the effect. So that, saving as, so I'm giving the name as it is, that is gallium, because in FDF file I have mentioned this file as this species is gallium. This is gallium.psf, and the second is that oxygen oxide using gallium. So this is that oxide one, and with that system we are going to use this. Yeah, that GJ we are using. So saving is this, and again I'm using, either you have to mention the same name in your species, or during saving that mention this here. So now we have two pseudo potential file corresponding to two species. So since I am mentioning here this gallium arsenide, so the output file that will show like this. And now I'm going to run system, and the command. So download first this pseudo potential file, then I am giving the command. So command is mpi run -np4 system, and then add your file name, FDF, and T result. This is the command I am using here. Use this. I think everything is good, because I have just downloaded this from website. So let me do this. Something is okay. Sorry, I have given this wrong file name. So gallium arsenide is here. Sorry that. This is the actual one. Now let me enter this. Again, there is some error. Number of processor you have to select. What should be there? I think that the pseudo potential is not proper for this. So let me try with the first another pseudo potential with that gallium. So that semicolon is not taking. This one with semicolon. This is LDA. This is GTA. So this type of error may appear anytime. So don't worry. Just I'm using this. And that's pseudo potential. It's basically very sensitive with that pseudo potential. Still there is NP and run NP2. Gallium oxide the TTF file. Let me delete all these. Right, so NP. Subscribe. Six. 6 days okay. That is okay. There I need not finding this. 6 days not. Let me use series version. Other version is not.
Excuse me, sir.
Yeah.
Sir, PSF of arsenic is not there. It is written as 0.psf. Sir.
Okay. Yes. Okay, yes, I'm using oxygen in spite of arsenic. So yeah, good. Thank you. Uh, so gallium, in spite of gallium arsenide, I'm using gallium oxide. Ah, good one. My mistake. This is that. Oh, I have to use arsenic. Wrong PSA file I was using. Thank you, dear. Yeah, it's still there is 0.
Sir, I think that, there might be some double negative sign before oversubscribe, sir.
So this is the series run. Let me try again. Okay, try in your system. Ah, so I can make mistake. So with a single processor, it will definitely run slow. So this is that SF convergence test. Our 4 atoms in the series single point. This has been completed. Oh, number of points is more. So that in FDF file, if I'm using number of points more than 1, then this will take. So here this number of CG points I have taken as 500. So let me first take this as 0. Control C. Anytime you can break your program and yeah, yes, I forgot to write one for parallel. Yes. Subscribe. Yeah. Single point calculation is starting. So so that this 1222.04, that old commands, that only NP, it's not working. So if you want to use your all the processor, then you have to use that oversubscribe term here with a single or double slash, and then definitely this will run faster when compared to series one. So I'm giving both commands uh, for the series. Yeah. So by using above arrow, you can get this line on your screen. So I'm just copying this. This is the parallel command. For parallel, use this. And series, is no need to give this. So test these two first, and then we will proceed about that structure. So designing that structure, that part is we will get this the lattice coordinates and lattice vectors for that. So before this, please complete this one, and when completed, just report here. So note down these commands on your memory book or somewhere. Frequently, you have to use these commands, and we are going to use generally that the parallel version of system. So the first command MPI run with word subscribes. MP is number of processors. So out of 8 processor, I am giving 6 processors to run this file. And this oversubscribe, this is one additional term used in 12.22.04. Before that, this oversubscribe was not needed. Yeah, Dr. Arun Kumar is here. Oh, good. Welcome, sir. Uh, Dr. Arun Kumar is going to deliver a talk on molecular dynamic simulation, and he is really one expert on hands-on session on system. possible errors, these are because of that absence of pseudo potential or some mistyping type of mistake, and that inability of that system identify bad commands. So these are that possible errors. Although that FDF file is a flexible data file, but sometimes it's a case sensitive too. Flexibility is you can give that the lines in any order, but method of giving it is fixed there. Dr. Gaurav, check the lab whether they are successfully completed or not. So should I proceed now? So I think I should proceed. Although this session was devoted to designing of the material, but it's already 12:40 and we have just completed one single system. Okay, anyway, no issue. So what we have to do for the first system run, you have to create FDF file, and that FDF file creation, the methodology I have mentioned this. Download that CIF file. This is for the crystalline one, and then open that CIF file, and by using GTIS, convert that GTIS file into FDF file, and then modify that FDF file. That is the default file generated by GDIS. So modify that FDF file by using the template I shared you, and then you can modify that structure. This is that structure, and by using this GTIS itself. So just some exercise I am trying to do here. So just a minute. So the first exercise that was related to FDF file creation for the first assistant, that is really important one. And then the next one is just we have to redesign or manipulate or modify that structure. So the second one is let's try to create that supercell. So generally when we go through some literature, then one line is mentioned in that literature, that is this particular study is performed by 2x2x2 supercell or 2x2x1 supercell. So how we can create that supercell? So first exercise is that the third exercise is that we can create that supercell. So this is that file, gallium arsenide hexagonal file, and we can rotate this by using your mouse right key, dragging this one, and to extend its structure we are going to use here. And first that view part is here, so we can view it in different direction as I mentioned earlier. And then I'm just going to convert this in form of supercell. So here I'm going to use this term, that is image, and I want to create that 2x2x2 supercell. So here that line 1 1 1 is given. So I'm just converting this, that is 2. So this will now extended 2 along x-axis, and then along y-axis let me again create 2. So this is now extended along, so x-axis and y-axis it is extended 2 times, and then z-axis, so along z-axis so this that extended structure that is 2x2x2 supercell. But here that when we view this one, so along x-axis this will look like this, that is yz plane. Along y-axis this is that structure, and along z-axis this is the structure. So in all three direction it has been extended 2 times, but still it is not created that supercell. In order to complete this one, we have to do one more exercise, that is we just go to this tool and go to building, and then this editing, and here some lines are mentioned. So here that next supercell is here, so just let me create. So that's after clicking this, uh, this will now the supercell 2x2x1 of this gallium arsenide, and the total number of atoms, this becomes 32 out of 4. So initially that was the unit cell was 4, so it extended 2 times along x-axis, y-axis, and z-axis. Then this becomes 2x2x2 supercell, and having now 32 atoms. So just you can save this as a FDF file. So gallium arsenide 2x2x2 dot FDF, and this is that supercell we can create. So now perform this. Just I'm repeating what we have done so far. So let me open that the file, CIF file. I can open terminal, open that CIF file. So GDIS gallium arsenide .cif file I have taken from material project. Enter this, and this will open this structure. And in order to create supercell, I will go to image, then 2, 2, 2, and 3 direction. I have extended its length. And then I will go to tool, and then building, editing. And this window will appear, and I'm making it supercell. So do this exercise, and the rest of this exercise are new materials we will perform in the next hands-on session. So, but this supercell you can create and click here and there and try to understand the behavior of this GDIS. So try yourself and record. So you can try this for the other materials also of your choice. After saving that file, this is that again the raw FDF file, and you can modify the same system name. And use same template. Here and reduce this. And now you can run this file also. Anyway, so I am concluding now. And, try all these with yourself, and if you are interested, you can go through the channel, and there are similar videos will be there. And there is one playlist there with 5 minutes talk, and there that the designing part and others are also there. So that 5 minutes DFT with Dr. Mohammed, you go to this link, and you can get some similar small lectures on small exercises on Sista and related. So that's it from the studio. So go there and search this playlist, and you get this is all public, and I have lectures on that input file formation, and especially that designing. So go to that, and in the next session I will design some more structure, that nanotube, nano ribbon, and that doping and creating a defects, and that interaction of two molecules to also. I will cover all this in the next coming session. So thank you all. See you tomorrow.
Sir,
Yeah.
Thank you, sir.
sir, hello.
Yes.
Sir, in changing the dimension of the supercell in the FTF file, there are two blocks, sir, Monco's block and supercell block, sir. Do you have to change in the both these lines?
I'm not getting is that there are two blocks in FDF file. I have just a coordinates is changing, and that other things are there, and whatever that change you can observe in that FDF file. So that the chemical species, their coordinates and lattice vectors, these are there. What is the extra? Number of atoms increases starting from 4 to 32 or whatever that number you have taken. The default sections I have just replaced by my template, and key points I have reduced to save the time. Okay, that is 2 crush 2 crush 2 in spite of 6 plus 6 plus 6 I have taken. Try yourself, and in case of any error, just post in the group. Definitely we will deal with that. Okay.
Yes, sir.
Any other question? Okay, sir. So I think
Okay.
we will conclude the day. Thank you, sir, for this wonderful session. And we'll meet tomorrow again, morning, 10 o'clock. No,
Yeah. Yes.
sir, there is some change in the timing tomorrow.
Okay.
Actually, we have a PhD Viva. So I'll
Oh.
let you know, sir.
Okay. Tomorrow's talk is going to, you have to inform the speaker. No?